My background is actually I'm a mathematician. I was always fascinated by numbers, and I would say the first time I got really into computing was when I was probably about 10, and I had one of those build-your-own computer construction sets, which was actually based on electric equipment, not electronics, and switches, mechanical switches. And I built a computer I could play something like tic-tac-toe with, and I won. And I thought, will this computer be upset that I win? And I said, no, it doesn't make sense. And I think from that point on, my fascination with computing started. So my job at NERSC is, or actually at Lawrence Berkeley National Labs, is covering a lot of different areas. So in high-performance computing at NERSC, of course, we have on one end the production compute capability to make actually science possible, but at the same time working with the community to advance towards exascale computing. I'm also responsible for ESNet, which is a nationwide networking provider for the Department of Energy, and there are exciting new technologies being developed in the networking space, which may make science and maybe even networking quite different in the future. But my heart is, of course, still in computational science and computational math and applications. The project with Darmenta is actually interesting for the following reason. I have been watching supercomputing, of course, for more than 20 years, and I'm always a little bit disappointed that the range of applications has stayed very much the same. We've done climate modeling, and we've done high-energy physics, and we've done nanoscience and all these things already in the late 80s. And I'd like to move new areas closer to high-performance computing. And what Darmenta is doing is cognitive computing that's modeling the human brain. So I find this absolutely fascinating. And of course, I said my original fascination was, can the human brain beat the computer? So I'm still fascinated by this question. That's the fascination of working in a national lab, because you have the exposure with working with everybody, and I could come up with 3 or 4 really fascinating things. I mean, a lot of the things which are on top of everybody's mind is energy and climate, which has started the project, which is trying to model and understand better how the ice sheets behave. That's the Greenland ice sheet and, of course, the Antarctic ice sheet. And surprisingly, while they are acknowledged, a big part of our understanding of the climate relies on understanding what happens with the ice sheet. The mathematical modeling and the computational modeling has not yet been carried out to a sufficient detail to actually couple this to a global climate model. So this is fascinating because mathematically, what we will do is use something called adaptive mesh refinement, and so we bring mathematical technology to bear on one of the important social problems of today. On the other hand, there are projects which are just plain out fascinating because they are sort of driving our intellectual curiosity. So we have a project in astrophysics called the Palomar Transient Factory, which is in collaboration with Caltech and JPL, which is basically using scanning large portions of the sky and looking for unusual transient phenomena. And it was starting out looking for large supernova and supernova explosions, but the same technology can be used to see if there are other interesting phenomena out there. So who knows, maybe thanks to computers, database search, and integrating high-performance computing with machine learning, we can figure out new things that could happen in the sky. Of course, the biggest technology challenge and technology trend that we're currently facing is that parallelism has become inevitable. For 25 years, I've been in a community which has said, we'll have to do massively parallel, we have to do massively parallel, and nobody believed us. But now it is real, and everybody knows that because of multi-core and the multi-core revolution, future processes will be parallel, will be increasingly parallel. We have a new Moore's law that the number of cores will double every 18 months. So everybody has to deal with parallelism. Now, translating this to the high end means that today we have high-end systems which have 100,000 to 200,000 cores. If we project forward this type of growth in parallelism, then we will have a decade from now 100 million to 1 billion core parallel systems. And we have absolutely no clue how we'll actually program them. We actually have no clue in how application will scale to that level. Yes, we have worked in parallel computing for a long period of time, for 15 to 20 years. But what is different is that we have been stuck at the 1,000 to 10,000 way parallel level until, say, 2004, 2005, and gradually increased. But the next 10 years will be just completely different. Multicore is changing the problem in a very significant way. And I think not only is it the increased parallelism, but I think we also have not yet really arrived at any type of architectural standard. Today there are many, many different approaches and different solutions, ranging from GPUs and accelerators to many core proposals, to heterogeneous multi-core proposals. So there is an architectural variety that the community really has to face in the next 5 years, where it's no clear path to the future. Looking back, I compare this somewhat to the time in the late 80s, early 90s, when at that time the still very small parallel computing community was facing the question, how will we actually program these systems in the future? And we knew that the so-called killer micros will lead us to get massively parallel systems, but we didn't know that those would be message passing systems. There were other architectural approaches around. And I particularly find it fascinating going back to 1989, 20 years ago, and look at what people thought how we would program these systems, and they were of the order of a dozen different suggestions around. So I think the community has worked out the solution once, and we found a path. Something similar will happen. We'll have to explore 10, 15 approaches, and one of them will hopefully be the successful one. Well, what I would like to learn is that why the human brain is 1,000,000 times more energy efficient than computers. We operate at room temperature with only a few watts, and we don't even have to think about the megawatt to gigawatt that the exaflop computers may take. So that's one other thing that we need to figure out, that maybe the fundamental computational model that we're using today, which is based on 64-bit floating point calculations, which work really well for computational physics, may not be the right model to do cognitive tasks such as image understanding, scene recognition, having a conversation.